Today on AI Paper Slop, we are breaking down masked visual actions for unified world modeling from researchers at Stanford, UMD, and Harvard. Video generative models have incredible priors about physical dynamics, but they are passive. This paper solves the action conditioning problem by expressing robotic actions as pixel space masked motions. By fine-tuning a video model on just 15 hours of data, the exact same model can act as a forward model, where you reveal the robot's motion and it predicts the scene's response, and an inverse model, where you reveal a moving object and it predicts the robot behavior needed to move it.
Yeah, it is a total paradigm shift for any ML engineers or AI researchers listening today. I mean, we are talking about fundamentally changing the architecture of world models here.
So we just stated that masked visual actions solve this action conditioning problem.
Yeah.
But to really appreciate that, we need to understand why the current methods are failing AI researchers right now.
Right, totally. Because standard video models, I mean, they are just passive observers. They watch YouTube videos all day, basically.
Yeah, just soaking in pixels without actually doing anything.
Exactly. And to make them useful for robotics, past works tried conditioning them on all sorts of things, text, bounding box tracks, applied forces.
But raw motor commands, right?
Yeah, raw motor commands are a huge one. Like, say you have a vector of joint angles, $1 through $8 for a robot arm. People would just feed that vector straight into the visual model alongside the video.
Which is wild when you think about it. It's like trying to teach a professional dancer a new routine by handing them a spreadsheet of joint torque values, instead of just showing them a video of the first few steps.
That is a brilliant analogy. Yeah, why did we ever think non-visual conditioning was the best route for visual models? I mean, these inputs are so sparse.
And they're super embodiment specific too, right? Like a spreadsheet for a robotic dog means nothing to a robotic arm.
Exactly. And crucially, they are totally misaligned with the visual space where the model actually learned its physics priors in the first place.
Right, it learned gravity and momentum by looking at dense 3D visual patches, not by doing abstract math.
Yep. So it is essentially forcing the network to unlearn its intuition and rely on a translation dictionary that we bolted onto the side.
Okay, so since non-visual inputs are just, fundamentally flawed for this, how exactly does this paper translate physical action into a visual language the model natively understands?
Well, they introduced the concept of the binary mask. They call it $, and it is basically a spatio-temporal tensor.
A spatio-temporal tensor. So it has dimensions of time, height, and width.
You got it. It indicates which pixels are revealed versus which ones need to be predicted. And this all ties back to a really elegant, unified formula for the conditional distribution.
Which is just the probability of the entities in the scene, right?
Yeah, exactly. PB1, E2 dots in knowledge. It covers all the interacting entities.
So how does that give us both forward and inverse models from the same formula?
So for forward modeling, you take a subset, let's call it never $, and set it to the active entities, in this case, the robot.
Okay, so you reveal the robot's masked trajectory over time.
Right. And then the model simulates how the passive environment, like, say, a block on a table, reacts to that movement.
Gotcha. That is the forward model. So the inverse model must just be flipping that subset CR$.
Exactly. You set subset CR2 to the passive entities, so you reveal the object moving, like the block sliding, and the model has to hallucinate or recover the active robot arm's required motion to make that happen.
Wow. Okay, I just want to point out the architectural elegance here. I mean, active and passive roles are no longer distinct, separate neural networks.
No, they're literally the exact same parameter space.
They're just different queries passed to the exact same underlying interaction prior. It is so clean.
It really is. And because it is so clean, the compute and data costs are just, well, they are kind of unbelievable.
Right, so let's get into that. Because any practitioner listening to this deep dive into the source material is immediately going to ask, okay, how many thousands of GPU hours did this take?
Try 15 hours.
Wait, really? Just 15?
Just 15 hours of fine-tuning on masked examples, that is it.
That is practically nothing in the world of foundation models. Where did they even get the data for that?
They sourced it from Droid, which gave them about 1,000 real-world demonstrations. So you get all that messy real-world noise.
Lighting changes, weird textures, all that.
Exactly. And then they supplemented that with 4,000 simulated examples from RoboCasa to get more structural diversity.
So 5,000 examples total. That is a tiny data set for what they achieved.
It really is. But here's the kicker. It has incredible zero-shot capabilities.
Okay, I have to jump in and play skeptic here on behalf of the listener, because if we only train it on robot arms moving like active robotic entities,
Yeah.
how does it know how an object is supposed to move backward to infer the arm?
You mean for the inverse queries?
Yeah. If it never saw inverse examples during those 15 hours, how does it reverse engineer that zero shot?
Right. It sounds like magic, but it comes down to the base video model's pre-existing massive web-scale physics prior.
Ah, so it already watched millions of hours of YouTube.
Exactly. The researchers use models similar to one, which already understand that if a cup slides across a table, some physical force must have pushed it.
So the 15 hours wasn't about teaching it physics. It already knew the physics.
Precisely. The mask just acts as an attention pointer. The lightweight fine-tuning basically just taught it, hey, in this specific robotic setting, the thing applying the force looks like this gray gripper.
Oh, wow. That makes so much sense. So that is why it generalizes zero shot to passive objects and even across multiple unseen embodiments and diverse environments.
Yeah, it just taps into that massive latent physics engine that is sitting right there.
But relying on internet-scale generative priors brings up a pretty big issue. Like, how do researchers ensure the generated physics are mechanically accurate?
You mean avoiding the classic generative AI movie magic?
Exactly. Like, it might look visually stunning to a human, but if you try to run that hallucinated trajectory on a real $50,000 robot arm, a single pixel of physical inaccuracy could snap a gear.
It is a huge concern. And human evaluation is just too slow, and frankly, humans are easily tricked by visual sleight of hand.
Right, we just fill in the blanks mentally.
We do. So the team developed an automated, highly rigorous evaluation protocol using a vision language model.
Which VLM did they use?
Gemini 3.1 Pro Preview. They used it as an automated evaluator for the generated rollouts.
Okay, so they didn't just ask Gemini, does this look nice? They must have had specific criteria.
Oh, yeah. They engineered prompts to hunt for critical antipatterns. The big one they were looking for was ghost contact or weak contact.
Ghost contact. So like when the gripper just waves near the object and the object magically moves.
Exactly. The prompt specifically demanded that the gripper must visibly compress, touch, or physically couple with the object. If there is implied magic contact, it is an automatic failure.
What about when a robot lets go of an object?
Yeah, post-disengagement coasting. That was another huge anti-pattern. If a heavy block just keeps sliding on a table like it is on ice after the robot lets go, the VLM flags it.
Because it lost track of the friction. But wait, to evaluate physics at that millimeter level with a VLM, your ground truth data has to be perfectly calibrated, right?
It has to be flawless.
Yeah.
And the physical rigor on the dataset side here was intense.
How do they manage that?
For the real-world DROID data, they used table-mounted April tags to calibrate the exact pose matrices.
Oh, those 2D barcodes used in machine vision.
Yeah, those. They mapped the precise transform matrix between the robot base, the wrist camera, and the external third-person camera.
So they locked the visual space directly to the robotic train space. That ensures the ground truth data was mathematically rigid.
Exactly. And when you have that level of rigor, you can trust your benchmarks.
Let's talk about those benchmarks. Because if we have proven the physics hold up under VLM scrutiny, how does this actually perform against state-of-the-art baselines?
The quantitative dominance is honestly pretty staggering. They tested masked visual actions against baselines like Controllable, One Move, One 2.2 I2V, and traditional skeleton conditioning.
And what data sets did they evaluate on?
Across Behavior 1K, Droid, and their own real-world data sets, masked visual actions consistently beat all of them.
In standard metrics like PSNR and SSIM, I assume?
Yes, but more importantly, it dominated in LPIPS, which measures perceptual similarity.
Right, because PSNR can be ruined by a slight shadow shift, even if the physics are perfect. LPIPS actually measures if the generated video feels like the ground truth.
And the baselines just fell apart there, which proves the core thesis. When you force a visual model to interpret non-visual mathematical tracks, you create a massive bottleneck.
So, bringing this back to the listener, how does this impact their daily work? This isn't just an academic party trick, right?
Not at all. It's a highly practical deployment tool. First, there is policy evaluation. Since the imagined rollouts correlate so tightly with physical reality, you can test experimental policies in the model's imagination.
Without risking your hardware. That is huge. What else?
Model-based planning. If a robot has several candidate futures, you can feed all those masked trajectories into the forward model, score them, and rank the best path before the robot even moves.
Wow. And then there is action extraction.
Yeah, this is the big one. The inverse model is so good at recovering visual motion that the video model literally acts as the policy itself.
Bypassing traditional inverse kinematics entirely. You just prompt the moving object, track the generated gripper in pixel space, and execute it on the hardware.
It fundamentally alters the stack, but we do need to ground this excitement with a critical limitation directly from the paper.
Always important. What is the catch?
Like all generative models, the system learns the statistical correlation of object interaction, not true causal relationships.
So it knows that a moving gripper correlates with a moving cup, but it doesn't actually understand Newton's laws of mass and friction.
Exactly. It is highly accurate pattern recognition, not a symbolic physics engine. And practically speaking, it is completely bottlenecked by the inference speed of the base video model.
Right, generating high-fidelity video rollouts for real-time control loops is super slow compared to a lightweight multi-layer perceptron that runs in milliseconds.
Yeah, you are limited by how fast your hardware can run a multi-billion parameter diffusion model.
Still, drastically lowering the barrier to robust robot learning is a massive leap forward for the field.
It is, but it also brings up standard dual use and safety concerns.
Right, if a system can easily infer complex mechanical steps just by watching a video of the desired outcome, that could be used for unauthorized or physically unsafe robotic behaviors.
The safety rails at the deployment level are going to need to be as robust as the generation models themselves.
Definitely. And it leaves us with a fascinating and frankly slightly wild final thought to chew on. If physical intervention can be successfully abstracted as just a masked visual trajectory to tap into a video model's latent physics prior, where else does this apply outside of robotic arms? Could we use masked visual actions on overhead drone footage of human crowds to accurately model and predict group dynamics during an emergency evacuation? Or what if we take a video of a broken, jammed machine, mask out a single gear, and have the inverse model perfectly hallucinate the missing mechanical part required to make the whole system turn again?